Great, thanks. Hi, my name is Syrian Truong. I'm a PhD candidate at the University of Chicago. I'm in physics, and I'm working with Peter Littlewood, who says hi to Natalia Burloff and David Snoke and other people I'm sure I'm forgetting. And I also did work with Dr. Jason Kay from the Flatiron Institute. So this talk is on improved solvers for GPE-like equations. And yes, I realize GPE stands for Gross-Pitafsky equation, so I committed the faux pas of having equations there twice. But I think it looks nice. So for this presentation, it's in three rough steps. So the motivation, the algorithm, and future steps. Where the algorithm is mostly time-splitting numerical methods, where I'll kind of go over some Lee and Schwang versions, which is already in the literature. But I'll also give some quirks that happen when you have complex coefficients, which we think might be all right. So the start of the show, Gross-Pitafsky equation, you've heard about it before. And I'm going to touch on a lot of stuff that's already been said in other talks. But essentially, the Gross-Pitafsky equation is that equation one right there. It's similar in form to the Ginsburg-Landau equation or nonlinear Schrodinger equation. And it can be used to, look at various phenomenons and simulate wave functions of Bose-Einstein condensates, which is pictured there. Where in our formulation, this alpha term is the Laplacian term coefficient, the V is the potential, and beta is this nonlinear term coefficient. So there's a lot of solvers out there in literature that exist for the standard Gross-Pitafsky equations, but less so for Gross-Pitafsky like equations that have a little bit more quirks like complex potentials or complex coefficients and added noise terms that are not concentrated within the potential, and et cetera. So one such equation right here is presented. This is an equation that we would like to kind of simulate, and it'd be helpful if we have solvers that are a little bit more tailored towards that. And these quirks aren't just kind of a brain game. It's just it comes from real physical systems that have gain and loss or dynamical systems, things like that. Okay, so these GP-like equations are useful for a variety of fields, optical, condensed matter, critical phenomena physics. But in particular, we care about current research being done utilizing Polaris-Hahn Bose-Einstein condensates, in particular looking at trajectories going through, in, or around the vicinity of an critical exceptional point and or unconventional computing with light, as you saw before with, say, Polaris-Hahn Bose-Einstein condensates interacting and creating some hybrid analog computing systems. Here's a picture of a critical exceptional points, which I'll explain on the next slide. It's a figure from a paper in my advisor's group. All right. So just a little bit of background. Critical exception point is essentially where systems, such as like an exciton, polariton, condensate, experiences a critical point. So think that liquid vapor critical point stuff. And an exceptional point through the coalescence of the collective eigenmodes, which is induced by some non-Hermitian mechanics. It's helpful if you want to simulate a trajectory through and encircling the vicinity of a critical exceptional point to use a noisy driven dissipative Gross-Pitafsky equation because we find that these equations have simulate that type of system well. There's another image from a paper demonstrating critical exceptional points. So the reason why we want to look at that trajectory is because we want to see what the properties and dynamic instabilities that are happening around that region for these nonlinear systems. So there has been a little bit of work done utilizing dynamic renormalization group. Using the analytics, they came up with some new universality classes. But given the constraints imposed near these critical exceptional points, it would be helpful to get some numerics to support some of these claims. But if you do want to look at some of these claims, the paper's right there by Rio and Peter, critical fluctuations at a many-body exceptional point. Right. And even further, the solver could help with open research questions involving Polaris-Einstein condensates, with thanks to hybrid analog computing. So those interacting condensates that you kind of saw a little bit about before. And it's nice because the physics here is going to be a little bit more complicated with the presence of noise. If you want to read some stuff about that, there's a paper here for a PhD thesis, and I think that person was actually on a slide before. Right. And the reason why you want to even have that kind of computing setup in the first place is because sometimes some problems are more efficiently mapped or solved when you map them to the global minimum solving principles of these polariton bose-Einstein condensate interactions. And as you stated before, there's been a lot of work done for, or at least some work done for the analytical approximations of the tactics. But it would be nice if we can have some supporting numerics here to help support those claims. Thinking about how the physics is complicated with the presence of noise, is this actually better optimized over classical computing counterparts or too unstable to be practical in this context? Right. So to recap, this project involves creating an improved numerical solver for these Gross-Patafsky-like equations, which may or may not have multiple components, complex coefficients for the Laplacian operator or the nonlinear term, complex potential, or added noise terms that are not just solely within the potential. And although there's a lot of GPU solvers out there, most of them focus on standard UBs that don't really take into context these other little quirks. And these quirks are important because they come from motivation in wanting to solve systems that have stuff like critical exceptional points or these polar Bose-Einstein condensates interacting with each other to do this hybrid analog computing with light. So with that motivation noted, I'm going to continue on to the algorithm, where the basis of this kind of algorithm is based off of my old master's thesis, time-splitting numerical methods for Gross-Patafsky equations with complex coefficients and complex potentials. I did it a while back, but this project had been on hiatus and just barely started back up again. If you do want to see that paper, feel free to email me for it. For some reason, it's hard to find. All right, so let's go over the algorithm here. I'm going to have this overview thing that continually goes on for each step. And I'm going to go a little bit faster here because I kind of want to get to the meat of what I have to say. So much of this is kind of like already in the literature, but step 6B in particular has something different that I would like. But overall, this is just going to be a time splitting method. We're going to look at variations for Lee and Truong, which has to do with first or second order with respect to the error in the time steps, and also looking at those complex cases. So we're going to state the Gross-Patafsky-like equation that we want to simulate. We're going to solve for the initial operator and exponential-based solution, approximate via exponential expansion, choose the weights, which is the Lee and Truong part, define quantities that are important to the numerical simulation, kind of talk about how you want to scale things for computational cost reasons, and state the associated differential equations to the approximation. So when you split it up to a more Laplacian operator differential equation and the potential and nonlinear term differential equation. And then you go in and you solve that Laplacian operator differential equation, utilize that solution inside the differential equation for the nonlinear and potential term, and then you just repeat that until you reach the final type step. All right, so now that's the overview. Let's go into it. All right. Same as before, you see this Gross-Patafsky equation, nothing changed. Let's just note that, what the difference is between the standard case and the complex coefficient / potential case. So alpha, beta, and the potential are all real numbers in the standard case, and it describes, relaxation to Hamiltonian ground state behavior. But with the complex coefficient and potential case, the alpha, beta terms, and the potential may or may not be complex. This can describe, systems that are more dynamical or have gain and loss systems. They're not as simple as the standard case. Right. Then we solve for the initial operator and exponential based solution. So it essentially looks like this with equation 4. There's some. Yes. Which one? There may have been an error there. I meant more just so that this is not going to necessarily describe a gain or loss system when you don't have these complex. Yeah, for the standard case. Yeah, thank you. So, all right, where was I? Yes. So we're going to the exponential based solution. Here's where we kind of separate the two, or start to separate the two between the Laplacian term differential equation and the potential and nonlinear term differential equation. All right, then we approximate via the exponential expansion and choose the weights. So here's where you start to consider computational costs of what your objective is when you're choosing between these two different methods for Lie or string approximation. So as a reminder, the Lie approximation is going to be first order and the time step error, whereas the string approximation is going to be second order and the type step error. So obviously, if computational cost is not a concern, you want the one with less error, but you kind of have to weigh what your objectives are and what the computational costs are. You can see that these equations are very similar, 5 and 6. The difference here is that for 5, you do the full time step for the Laplacian operator differential equation and the full time step for the potential and nonlinear term differential equation, utilizing the solution from the Laplacian operator differential equation. But for the Schrödinger one, for the Laplacian operator differential equation, you first have half a time step, then go to the potential nonlinear term differential equation, use the previous solution, and then go back to a Laplacian operator differential equation and complete that last half time step for each full time step. All right. Okay, now we're going to find quantities important to the numerical simulation. So the stuff listed here is not terribly important. It's rather obvious what each of these are once you implement the code. The spatial domain, final time, number of grid points, number of time steps, grid's basic size, grid points, time step points, initial solution data. But we just want to keep in mind, how you want to optimize and scale things. Obviously, it would be great to have a lot of number of grid points, very small time steps, but you have to consider if this is computationally feasible or how you should orient each of these kind of components within the code. Then you station the associated differential equations to the approximations. So sort of what like I said before, 6a is going to correspond to the Laplacian term, whereas 6b is going to correspond to the differential equation for the potential nonlinear term. And each solution kind of feeds into the next, where we can kind of see for the string one, 10 and 12 shows that these go actually a half time step as opposed to equation 8 for the full time step. All right. So now we go into 6a, which follows the first differential equation of the Laplacian operator term. So this is mostly done with fast Fourier transforms. Kind of give the outline here. So you define the Fourier series and the Fourier coefficient in equation 13. You take that differential equation for the Laplacian operator on the left side of equation 14. You reorient it to get the right side of equation 14, plug that back into the top left of equation 13, and you get equation 15, which solves it for this differential equation part. But one thing you have to note here, and where it starts to differ between the standard case and the complex case. So if you have an alpha term that's, let's see, I can get my right. If you have an alpha term that is complex, then the imaginary part is restricted to positive values depending on what you want to do, due to the consequences from the exponential term. So if you have a negative exponential, this is going to turn into a positive, or if you have a negative alpha imaginary term for the alpha term, you get an exponential that's going to be blowing up depending on the value. Whereas if you have a positive imaginary term for the alpha term, it's going to be a decaying exponential. Right. Okay. Now for step 6b, which is the second differential equation, which has to do with the potential and the nonlinear term. All right. So we have equation 16, which is just that differential equation restated. You turn the crank against solve it to get to something that's equation 17, but then you get to a step where you have this integral with respect to that nonlinear term. So you have to figure out what that nonlinear term is with respect to time in order to solve. In the standard case, this is easier because if you do some math, which I have in the appendix slides, if anyone wants to see, you find out that its time dependency is equal to 0. So that makes that integral easy. You just pull it out and you solve it and you get equation 18. But if you have complex coefficients on the nonlinear term and or a complex potential, the solution's a little bit different because the time dependency of the nonlinear term is no longer 0. If you have both a complex potential and complex nonlinear term, it looks like this, where these squiggly lines are the imaginary terms of the potential or the beta term. Um, and you need to kind of plug that into equation 17 and solve for it outright to get equation 19. So this equation 19 is true for complex coefficients of the nonlinear term and the complex potential. If you have just a complex potential and not a complex nonlinear term, it looks a little bit different, but it's still different from equation 18, and you still have a non-zero time dependency. So you need to kind of outright solve for those. Yeah, and same for the vice versa case for the complex nonlinear term coefficient, but not complex potential. With that said, equation 19 and equations like it, if you have a small enough time step, it is going to be approximately the same as equation 18, but this is kind of a constraint here that we found. Right. And that out of the way, that's just the last step, which is basically doing step 6 over and over again until you get to the final time step and you get an equation that looks rather familiar, future line condensate or whatever you're trying to settle it. All right. Now for future steps, just to recap, what we've done is we're trying to prepare a numerical solver for GPE-like equations for utilizing research that is relevant to looking at the trajectory in and around and through critical exceptional points, as well as polariton bose-Einstein condensate interactions for hybrid analog computing systems. The progress thus far is that we've attempted modifications of a variety of current GPU solvers, but as far as we know, they all have some specific complications. Dr. Jason K and I had derived some necessary methodology steps for the Lee and Schrödinger time splitting method, which takes into account those complex Laplacian operator term coefficients, complex potentials, and complex nonlinear term coefficients. And next steps, we want to implement into the solver multiple components and non-potential based noise term features in order to get simulations of the example equation, which I'm restating up there. So we can simulate these critical exceptional point physics properties. We have a graphic here of kind of example of showing that this is not simple behavior that could be described by just like standard GPEs. You have these kind of coupled condensates that exhibit some extreme behaviors in this paper here, which they can explain it a little bit better than me. And the link's right there if you want it. Great. And I want to thank my advisor and collaborator, Dr. Jason Kay, my advisor, Peter Littlewood, others in the Littlewood group, and all those help. And thank you for taking the time. Thanks.
For plenty of time to prep. Right? So we save a lot of time. Thank you.
Yeah, no worries.
Looks like these were like 10. So
I knew people wanted to go to the waterfall.
yeah. Yeah.
Sorry, can you say that again? Yeah, you probably can. I mean, I'd imagine that changed the solution a little bit. But yeah.